So far, we've considered rigid body rotations. Now let's consider a general rigid body motion, which would consist of a translation and a rotation. So point A with position vector r sub A has angular velocity omega, angular acceleration alpha, and point B, which has position relative to A of RB relative to A, which would be RB minus RA. So the velocity at point B, V sub B, equals V sub A plus the velocity of B relative to A, which equals V sub A plus omega cross R of B relative to A, so the rotation about A. Similarly, for the acceleration, we can write that A sub B equals A sub A plus A of B relative to A. This is A sub A plus alpha cross R of B relative to A plus omega cross R of B relative to A. So in other words, the most general motion of a rigid body is equivalent to a translation defined by the motion of a reference particle, in this case A, and a rotation about the fixed point A. Let's consider a two-dimensional example of a general plane motion consisting of a translation and a rotation in a plane. So A1 goes to A2 and B1 goes to B2 as this body translates and rotates. So the translation we can show as the vector connecting A1 to A2, and there's a parallel vector connecting B1 to B1 prime. Then to get from B1 prime to B2, this must be a rotation. So considering this a little bit further, if A has velocity VA and B has velocity VB, that can be decomposed into the sum of the translation where A and B both translate with a velocity of VA, plus a rotation of B about A with an angular velocity omega. So this is the velocity of B relative to A, which is equivalent to angular velocity omega, referenced to a new reference frame x prime y prime that has A as its origin. So we've said that a plane motion can be represented as the sum of the translation of an arbitrary reference point, in this case A, and a rotation about that reference point. And we can write for the accelerations similarly that A sub B equals A sub A plus A of B relative to A. And the tangent component of the relative acceleration is R alpha. And the normal component of the relative acceleration is R omega squared, where R here is measured from the new origin at A.